Hello. Sometimes when we are reading some papers and it's quite difficult to understand some concepts such as algebra or sigma algebra or Borel sigma algebra, right? And also there are a lot of different measures that we can see in the some theorems of the papers, and some of those measures are called probability measures, right? And some are other general measures. Okay, so what do those concepts mean, right? So in this video, we'll discuss the basic idea behind those pretty fundamental concepts in the algebra and measure theory. So we'll just give a brief introduction of those to have some basic intuition of those things to help us better understanding the papers. Okay, so basically, so a measure is nothing but a function. Okay, so measure is just a function that satisfies some properties. Okay, so it's just a function satisfying some properties. Okay, so it's nothing special, it's just functions. Okay, so probability measure, so from the name, then we can know that this is something that we use to measure the probabilities, right? So some functions to measure the probabilities. So we will put some requirements to this function to let it to have some properties that we can measure the probabilities, right? So that's the idea of measure, probability measure. And so algebra, so we will talk about the sigma algebra later. So basically an algebra, okay, this is just something, okay, is a collection of subsets that satisfy some properties. Okay, just a collection of subsets that satisfy some properties. Okay, so with those pretty simple intuitions, then we can begin our rigorous definitions for those things, right? Okay, so now let's look at what does the sigma algebra mean. Okay, so sigma algebra, like we said, is just a special kind of algebra, right? Some it's just some subsets that is satisfying some properties, okay, that we need. Okay, so the definition of sigma algebra, okay, so a collection of subsets. So this curly A, okay, so it's pretty different from the standard A. So this curly A is a subset of the power set. Okay, so this is like sort of curly P. It's not the standard P. So this is the power set, okay, of some omega. Okay, so this collection of subsets is called a sigma algebra, okay, if it satisfies some properties. Okay, so the first is that the empty and sigma itself, they both belong to this A. Okay, so basically we can see that this the algebra, this thing basically means that it satisfies some properties, so we can manipulate, or we can use the algebras, right? So use the math, the algebras to calculate something. So it satisfies some basic properties, right? So that we can use those things to calculate something. Okay. So if so the second is that if a set A, so this is the standard letter, capital letter A, in this curly A, okay, then the complement of A, okay, so by definition is just the omega is excluding A. Okay, so that is also an element of this A. Okay, so both A and its complement are in this A. Okay, so that's pretty normal requirement. And the third thing for the sigma algebra is that if A1, okay, A2, dot, dot, dot. So if all of those, they all belong to A, okay, then, okay, the union of all those sets, okay, this is also in this A, okay. All right, so that's it, right? So those are all the properties that we need for this collection of the subsets to be a sigma algebra, okay. So that's pretty simple, right? So now this is not mysterious, and we just can understand this, right? Pretty straightforward. Okay, so that's sigma algebra. So what is Borel sigma algebra? Okay, we can sometimes we can see this in some papers, right, with the probability or something using the measure theory or the sigma algebra. So you can see this Borel sigma algebra. Okay, so this is just a sigma algebra. Okay, but which is generated by some open sets. Okay, by some open sets. Okay, in the real numbers. Okay, and we often use this curly B to denote the Borel sigma algebra. Okay, so this Bx, okay, so this should be sort of a B omega, right? Maybe we just skip that. Okay, so basically this Borel sigma algebra, this thing is already big enough. Okay, so the reason that we cannot directly use the power set P, okay, so let's say this Borel sigma algebra, right, sometimes it's already big enough, and the power set, okay, it sometimes the reason that we cannot use that is because the power set of some set is it cannot fulfill some properties that we need for the measures, right? Cannot fulfill some properties for the measurement. Okay. All right, so that's why we need the sigma algebra, and okay, and so the Borel sigma algebra is just a special case of the sigma algebra, right? So it should be a special case of that, and this Borel sigma algebra is a sigma algebra generated by a. Okay, so let's put this in details. Okay, so a Borel sigma algebra is a sigma algebra. Okay, generated by a collection of subsets of omega. Okay, and whose elements are finite open intervals on the real numbers. Okay, so that's the definition for a Borel sigma algebra, right? So that's pretty simple, straightforward. So this, in turn, this gives us the smallest sigma algebra containing the omega, right? So this gives that would be the most efficient one, right? So that's the smallest sigma algebra containing the omega. Okay, so that's Borel sigma algebra. Okay. All right. So next, we want to discuss what does the probability measure mean. Okay. So we know that measure is just a function, right? So it's a function satisfying some properties, right? And we can have a lot of different kinds of measures, and we don't want to introduce all those measures, but we want to focus on the probability measure. Okay. So now let's see what does this probability measure satisfy. Okay. All right. So we have the definition for that formally. Okay. So let this curly A again to be a sigma algebra. So this thing should be a subset of the power set of some omega. Okay. As a sigma algebra. Okay. So a map or a function, this P, okay, with two legs, this P, okay, which is a map from this curly A to 0, 1, okay. So we know that probabilities are the numbers between 0 and 1, right? So that's where that is where the this probability numbers coming from, right? So this is called a probability measure if we have the following requirements satisfied. Okay, so the first one is that this P, okay, P omega, so this should be 1, right? So everything together, we have the probability of 1. And the P of empty would be 0, right? And the second is the additivity, okay, or it's called sigma additivity, okay, and that's why we need this as a sigma algebra, right? Okay, sigma additivity for pairwise disjoint sets. Okay, so it means that P union AJ, okay, should be the summation of the P's separately, okay. All right. Okay, so pairwise disjoint sets means that AI union AJ is empty for any I not equal to J. Okay. So that's it. So this is all those requirements for this measure, for this function. Okay, right? So this is just a function, essentially. So for this function to be a valid probability measure. Right? Okay, And this is very straightforward, right? Because and we can consider some examples later to show that the basic properties for the probabilities, right? Okay, so now let's have this example. So let's suppose we're throwing a die, okay, just one throw, die, okay. So this omega space, the set should be 1 to up to 6, right? So 6 kind of faces of a die. Okay, so this curly A will be the power set of omega, okay, as the definition we mentioned. So this P is a map from this A to 0, 1, okay. So let's say P of some A event is just the cardinality of the set or the cardinality of the omega set, right? So let's say the probability of having 1 would be 1 over 6, right? Or the probability of having a even number, 2, 6, or 4, would be 3 over 6, 1/2, right? So that's the example, and this is the idea of the probability measure, right? Okay. All right, so in this video we discussed the briefly discussed the meaning of the sigma algebra, borrow sigma algebra, and the probability measure, right? And those are some useful notations and some definitions for us to know when we're reading the papers, right? Okay.